This video is a review of exponential and logarithmic functions. We'll start by talking about exponential functions. So for a definition here, an exponential function has the form f of x equals a to the x power, where x is any real number and a is greater than 0, a doesn't equal 1. So that's the general definition of it. Let's just talk about different pieces. A is what we call the base for the function. A has to be greater than 0. A is not equal to 1. X is a variable, right? This is the exponent or the power, however you want to describe it. But in this case, the base will be a constant and the variable is in the exponent. So when we look at an exponential function, right, the key is that this base has to be positive and it doesn't equal 1. The reason it has to be positive is that, you'll have some issues with the sign. If this was negative and you had this being raised to a power, and that power kept changing, sometimes that value would be positive, sometimes it would be negative. It wouldn't be a continuous graph. For a not equal to 1, if 1 was the base, then this would just be 1 to the x, and 1 to any power other than 0, or 1 to any power actually, would just be 1. So you wouldn't have any exponential function, you'd actually have a linear function. So some examples of what this looks like, right? So we're not going to really do anything with these, just to make sure you understand if you're looking at them. Right, for this example, if I said something like f of x equals 4 to the x, right? So 4 is the base, x is the power. I could say something like g of x equals, it could be a fraction, 1/3 to the x. And you also might see things that have, a coefficient in front. So if I say something like h of x equals, 5, and then, times 3 to the x power. It's still an exponential function. It's just that this has a coefficient of 5 in front. Let's take a look at an example where we graph it. So if I was to say, let's graph f of x equals 2 to the x power. Okay, so we'll try to graph this, and we'll graph it by plotting points just so you have an understanding of what the graph would look like. So when I go to graph this by plotting points, remember f of x is the same as saying y equals. So this is like y equals 2 to the x power. And I'm going to pick out x values and then find the corresponding y values. So I'll set up a little chart here. Here's x, here's y, which equals 2 to the x power. And then we'll put the ordered pair x comma y here at the end. And the first value I'll sub in, I'd like to pick things to the left of 0, at 0, and to the right. So I'll start with x equals -2. Well, then y would be equal to 2 to the -2 power. Make sure you remember how a negative exponent works. It's not -4. You don't just take this and make it the sign. A negative exponent, remember, is 1 over whatever the base was, and then make the power positive. So it's 1 over 2 squared, which really is 1/4. So the first point we'll be looking at is -2, 1/4, and that'll be on our graph. And we'll sketch this in a minute. In a similar way, right, if I said x is -1, then we'd have 2 to the -1 power. Well, that's 1 over 2, which is 1/2. So this would be -1, 1/2 is on our graph. The next one we would look at, let's say x equals 0, 2 to the 0 power. Remember, anything to the 0 power is always 1, so this would be equal to 1. So we have the ordered pair 0, 1. And then we'll sub in just a few more. If I said, x equals 1, then we'd have 2 to the 1, which equals 2. So we have the point 1, 2. When x equals 2, we have 2 squared. So the y value there would be 4. So we would have 2, 4. And we'll just look at one more. If I said for x equals 3, we'd have 2 to the third power. Remember, that means 2 times 2 times 2. 2 to the third power gives me 8, so we'd have the 0.38. You should know how to substitute these in your calculator. If you used any of these in your calculator, you get decimal numbers for the negative values in this case. But let's plot the graph. So, we'll look at this on a grid here. We'll assume that all of our values are 1 apart on the axes. So we have an x-axis and a y-axis, and let's just think about where the points are. So if I was looking at -2 1/4, the x value -2, the y value 1/4 would be just above the axis there. If I was looking at -1 1/2, well, -1 1/2 would be right about there. 0 1, right, that's going to be what we call the y-intercept, right? It crosses the y-axis there. 1 2, the x value of 1, the y value of 2 would be there. 2 4, so 2 comma 1 2 3 4 would be there, and 3 up 1 2 3 4 5 6 7 8 would be there. And so we have this curve. And I'll sketch it in just a second. One thing I want to point out is that will you ever actually touch the x-axis? In other words, will the y value ever be 0? And the way you kind of know that it won't is, if you sub in values greater than 0 for x, right, going this way, these y values are getting higher and higher. They're getting larger and larger, right? It'll be 2 to a power that's getting larger and larger. If you sub in 0, right, we know 2 to the 0 power gives you 1, so we know where that is. And if you subbed in negative values for x, you'd have this as, 2 to the -2, and that's going to be 2 to the -3, 2 to the -4. So it'd be 1 over a number that's getting really big makes those numbers get smaller. So these numbers would get smaller, but they would never actually equal 0 because 2 to a power, right, a positive base to a power, can never become 0 because any power I pick won't give me a y value of 0. So we have this, what we call horizontal asymptote, right? And this equation of this is y equals 0. Horizontal asymptote, I'll use HA to just abbreviate that. And so what's really showing is that our graph approaches this, but never actually touches. And put arrows on the ends. So this is the graph of f of x equals 2 to the x. So, like I said, the graph never actually is going to touch the axis here. If you're taking the limit as x went out to -infinity, the limit would be 0. But it doesn't actually ever equal 0 in terms of the function value. A couple things to note here, all right, just generally speaking. If you have a graph that has a to the x, right, and a being, like in this case 2, a being a number greater than 1, the graph will be increasing. It'll be moving upward from left to right. So that's the sketch of f of x equals 2 to the x. Let's take a look at another one. We'll look at, if I said to graph, maybe I'll do it right here next to it. So for this example, if I said to graph, we'll call it g of x equals 1/2 to the x power. So, if I'm looking at this, it's a little different than the previous one because I have a fraction for my base. Still meets the requirements for an exponential function because it is greater than 0. And really, I'm going to go through and plot points similar to how I just did. One thing to notice is that if I have this is equal to 1/2 to the x power, I can really rewrite this. You can rewrite 1/2 as 2 to the -1 power raised to the x. And if you have a power raised to a power, you can actually multiply the exponents. This is actually the same as saying it's 2 to the -x power. So these are equivalent, all three of these. What's helpful is if you have this 2 to the -x, it might be easier when you substitute values in to see what happens. So we'll kind of do that now and see what that looks like. So we'll have an x value. We'll have y equals 1/2 to the x power. Just remember that's the same as saying 2 to the -x. And then we'll have an ordered pair x comma y. So we'll pick x values. I'll start by picking x to be -3. The y value that would go with that would be y is equal to, well, you could say 1/2 to the -3, which really is the same as saying 2 to the negative 3, and that might be easier to work with. 2 to the negative 3 is just 2 to the third power, which equals 8. So we know that we have the point -3, 8 in terms of x comma y. And, you know, if I pick x to be -2, then I'd have 1/2 to the -2, which is the same as 2 to the -2, subbing into that, gives me 2 squared, which equals 4. So I have -2, 4. When x is -1, we'd have 2 to the -1, which is just 2 to the 1, which equals 2. So this would be -1, 2. When x equals 0, right, you could have 2 to the -0 is just 2 to the 0. Anything to the 0 power, remember, is 1, right, for any base other than 0. So we got the point 0, 1. And let's do a couple more. If I was substituting in 1, we'd have 2 to the -1, which is the same as 1/2 to the 1, right? So that equals 1/2. So we would have 1 comma 1/2. And then the last point I'll look at is 2. So we have 2 to the -2, which is the same as 1/2 squared, right? Or 1 over 2 squared, which equals 1/4. So we'd have the point 2, 1/4. So something to notice here is the points that we just found, right, are really, you know, corresponding to the ones we had here. It's just a reflection, right? The negative on the x really just changed where the y values would be associated. This was at 3,8, it's at -3,8 now. This was at 2,4, it's at -2,4 now. This was at 1,2, it's at -1,2. So what you're actually seeing here, and you may have learned it in previous courses, is that the x's being negated will give you a reflection over the y-axis. And we'll see that in the graph that we're going to do in just a second. So these are the points we have. If I was to graph this, maybe I'll graph it on the same grid that we graphed the last one. So I'll look at this right here, and we'll plot the points. So the first point we had was -3,8. So for -3,8, -1, 2, -3, up 1, 2, 3, 4, 5, 6, 7, 8 is right there. -2, -4, so -2, and then up 1, 2, 3, 4. Sorry, -2, +4. -1, 2, so -1 up 1, 2 would be here. 0, 1. 0, 1 would be right at that y-intercept, and 1, 1/2 would put me halfway in between there. And you know, we have 2, 1/4, so 2, 1/4 are getting closer and closer to the axis. Again, though, remember, you're going to have this horizontal asymptote in here, right? The horizontal asymptote is a line you're never going to touch. You'll get smaller and smaller, but you'll never actually get to that value. So when I go to sketch this, right, it's a curve, goes through these points, arrows on the end because it does go on forever in both directions. In other words, you can sub in x values for all real numbers, and you can get a y value out. And this is the function g of x equals 1/2 to the x power. So, you know, you can see that reflection over the y-axis I was speaking of a little while ago. The thing to notice here is that if your base a is between 0 and 1, then this function is always decreasing. So these are some general properties of the exponential function that you might want to remember. So maybe I'll just write them down here just so you have it as a note. If I just said note for f of x equals a to the x, if a is greater than 1, f of x is increasing. If 0 is less than a is less than 1, right? If our base is between 0 and 1, then f of x is decreasing. And then the other thing that you might note is that your y-intercept is always going to be at 0, 1, because when, you know, x x equals 0, the base to a power will give you a y value of 1. So 0, 1 is the y-intercept. Alright, and horizontal asymptote for at y equals 0, right? The line that you approach but never cross. So, this is a general way of graphing exponential functions. They all will have the same type of shape that we just saw. If a is greater than 1, it'll be increasing like this. If it's between 0 and 1, it'll be decreasing like this. A lot of the times, what we'll talk about in calculus is we'll use the natural base e. And you may have seen the natural base e before, but let's make sure we just refer to it here so you know what we're talking about. So the natural base e is an irrational constant. When I say it's an irrational constant, think about it like pi. It's going to be a number that has a decimal that goes on forever without a pattern. For us, if you want to approximate what e is, your calculator can do that for you. But we're going to use e typically. So if I had, see the second key on the ln, so if I had second e, and then I'm just going to put e to the 1 power, which is the same as saying e. You notice you get this number 2.718281828. It doesn't repeat forever in the same pattern. It kind of looks like it right there, but it really doesn't. So we say e is approximately 2.718. We'll use our calculators to get the value for e when we do it in an applied example. You wouldn't ever use like a rounding of 2.718. You'd actually use the e button on your calculator. Just making sure you understand that this is an irrational constant. We see it often show up in applied examples, and we'll do that a little bit later. But the thing that it relates to here is that, for example, if I had the function y equals e to the x, this meets our requirements for being an exponential function. It's a base, right? That's a constant, right? Greater than 0. Another 2.718 is greater than 0. And it's raised to a power of x, which is the variable. If I was to just do a quick little sketch of this, and I'm not going to be accurate about it because the numbers don't come out to nice values to graph, but the point is that, we know that a is greater than 1, and we know it's exponential, so we know it's going to have a y-intercept here at 0, 1, and it's going to look like this. It's going to have this shape. Where these x values are, if you sub in an x value, the y values will be at irrational values, and that's okay. You would just want to plot them where they belong if you were to graph it. But just have an idea of what it looks like is important here. We'll also talk about logarithmic functions, which really relate very closely to exponentials. They actually are inverses of one another. I'll give you the definition, and then we'll do an example where we might sketch one. So for this definition here, we'll say a logarithm is defined as, and you may have heard logarithms called logs before. I'll write it as y equals log base a of x. Now, when I say that, let's make sure we understand, right? So this is log, this is the base, right? So y equals log base a of x. What this really means, it really is telling you how to write this as an exponential. Logs are always equal to an exponent. So the y here is actually going to be the exponent on the base. So this really means you want the base a to the y power, which is the exponent, and it's going to be equal to whatever you're taking the log of, the argument of the log, which equals x. So this base a is telling you to rewrite it as a base here. This y here is telling you that that's going to be the exponent. So logs are always equal to exponents, and then this x, right, that's going to be what you're equal to. Right, this is what we would call the argument for the log, but it's going to be equal to the value for the exponential. All right, so the way you would read this, remember, is log base a. And just like for our exponentials, since logs are really exponentials, right, this is what they're really showing you here, right? Logs are always equal to the exponents for your exponential. It has the same properties in terms of our base. Our base, you know, where a is greater than 0 and a doesn't equal 1, because of the same reasons we talked about with exponential functions. So you might see this written as f of x equals log base a of x. Remember, y and f of x are used interchangeably. For logs, you know, this base will change if you pay attention to what it is. I'll do an example where we graph one now, just so you see it, and then we'll talk about using this. So if I said to graph, and I said I'll call the function h of x equals log base 2 of x. First thing you should notice is that when I say h of x equals log base 2 of x, h of x, remember, is interchangeable with y equals log base 2 of x. And before I graph this, what I really want to do is I want to change this to an exponential. So I'm going to rewrite this. All right, so RW here means rewrite, right, as an exponential. If I rewrite it as an exponential, what does this really give us? Well, remember how I just said it above. I say, what's the base? Well, the base is 2. What's the exponent? Well, the log is always equal to the exponent, so it's 2 to the y power, and it's equal to whatever the argument of the log is, which is x. So you have 2 to the y equals x. Now, when we graphed earlier, we were picking x values to find y values, but in this case, it's actually easier if we are to, you know, pick the y values first and get the corresponding x values, because then you can just say x equals whatever the number comes out to. If you were to pick the x values first, you would want to pick perfect powers of 2 to make sure it works out nicely for you. Otherwise, we don't know how to solve that yet, and we can talk about how to solve it, but you wouldn't get values that are easy to graph. So when we go to sketch this, right, to get our graph, what I'm really going to do is I'm going to set up my chart with, here's x, right, x is equal to 2 to the y, and then here's y, and then I'll put the ordered pairs here still as x comma y, but I want to make sure you have an understanding that the way we're going to pick out what y is, right, so we pick the y values first, and then we're going to get the corresponding x values. So in doing that, all right, I'll just pick values to the left of 0, add 0, and to the right of 0. So for y, I'll pick, let's say, -2 to start. Well, then x is going to be equal to, we've got 2 to the -2 power, which equals 1/4, right, because it's 1 over 2 squared, so it's 1/4. So the coordinates would be 1/4 comma -2. And then we'll pick the next value here. I'll pick y to be -1. Well, then we'd have 2 to the -1, which equals 1/2. So the coordinates, remember, x comma y is 1/2 -1. The next value I'll pick for y is 0. So I'd have 2 to the 0 equals, well, that's just 1. So we'd have the point 1 comma 0. The next y value I'll pick is 1, so I'd have 2 to the 1, which equals 2, so this would be the point 2, 1. And then I'll pick one, maybe 2 more. If I said I picked y to be 2, then we'd have 2 squared, which equals 4, so the coordinates would be 4, 2. And then if I picked y equal to 3, I'd have 2 to the 3rd power, right, and we sub in for y there, which equals 8. So I'd have the point 8, 3. So these are giving you values that you can plot on your graph. When I go to plot this, right, looking at these values, 1/4, -2. The x value is 1/4, so you're going to assume these are all one apart. You're barely moving away from the axis. -2 would be right there. 1/2, -1, you know, you'd be halfway in between for the x value. The y value is -1, you'd be there. 1, 0, the x value is 1, the y value is 0. That's actually the x-intercept, right? It crosses the x-axis there. 2, 1, the x value is 2, the y value is 1, would be here. 4, 2, so the x value of 1, 2, 3, 4, the y value would be 2. And 8, 3, so the x value of 8, the y value of 1, 2, 3 would be there. And you have a curve, and you'll draw through it, arrows on the ends. Notice you get close and close to this y-axis, but do you ever touch it? In other words, does x ever equal 0? Well, no matter what I pick for y, right, x is equal to 2 to the y, the base is a positive number to a power. This will never become 0. So we have, in this case, what we call a vertical asymptote. I'll use VA to abbreviate it, at x equals 0. All right, it's going straight up and down through 0. The curve then, so it approaches this but never touches, arrows on the end. It curves through here, through those points, arrow on the end. This goes not only outward forever, but upward forever. It's just going very slowly. And this is the graph of h of x equals log base 2 of x. So what I want to point out here, since we have both graphs here, for f of x equals 2 to the x, or y equals 2 to the x, and y equals log base 2 of x, these functions are actually inverses of one another. This green function here and this blue function here. And you can kind of see it, the x and y values really just get switched, right? And that's how when you find an inverse for a function, typically what you do is you switch the x and y values. It's a reflection over the line y equals x. And if I switch those, right, switching the x and y values switches the asymptote, and then switching these values for x and y gave us these ones. You can actually see that these points here are the coordinates reversed from what we had on the first page. So when you have that, right, so logs and exponentials are inverses of one another, and you can kind of see it here, right? If I was to switch x and y, that would give me y equals 2 to the x, which is what we would have graphed here. So they're inverse functions of each other, and that's important to know. But the way you graph the log function is really picking the y values first and then finding the corresponding x values, but you have to rewrite it as an exponential to do that. You know, similar to the properties of the exponentials, we can talk about properties for logs. You know, if I should say for, all right, so for f of x equals log base a of x, if a is greater than 1, f of x increases. If a is between 0 and 1, then f of x decreases. And what would happen on our graph is that it would actually, the asymptote would be approached going upward towards it and then coming down through and going away this way. The point 1, 0 is the x-intercept, and you have a vertical asymptote at x equals 0. So those are the properties for logs. It's important to understand where they come from. We're not going to do a lot of graphing in calculus using these properties, but these are properties that you're expected to know, and we can refer to when we think of some of the functions we're going to look at. You know, just like we had y equals e to the x earlier as the natural base, we can have logs that have a natural base. The natural base for log, all right, is base e. So we use a shorthand notation for that. So for what we do, you know, if we have log base e, right, so log base e of x is the natural log, and we write that, all right, so this will be written as, and the way we would write this is ln of x. So when I say ln of x, that ln stands for log base e. right? It's a shorthand way of writing it. So that means a natural log. So a natural log is what we call log base e. So make sure you know when you see ln, we're just saying the base of the log is e. So we can use these log properties to rewrite exponentials and vice versa. So we'll take a look at a couple examples like that, just making sure we understand how to do that. So if I said, for example, rewrite each as an exponential. Well, for this first one, if I said log base 3 of 81 equals 4. Remember, we rewrite logs based on what we said earlier, right? So let me just bring it back up for a second. Y equals log base a of x means you write what's the base? The logs are equal to the exponent, and then the exponential is equal to whatever the argument of the log is. So if I'm looking at log base 3 of 81 equals 4, if I just want to rewrite as an exponential, you should ask yourself, what's the base? Well, the base is 3. What's the exponent? Well, the log's always equal to the exponent, so it's 4. And then what's the exponential equal? Well, it equals the argument of the log, which is 81. Now, this is just us rewriting it. There's really no work to do here, right? 3 to the 4th power does equal 81, but there's nothing to do in terms of solving here. Later on, we'll talk about how you would solve these, but this isn't a question where they're asking you to solve. If I wrote this, if I wrote log base k of t equals 12, how would I rewrite that? Well, what's the base? The base is k, so we start with that. What's the exponent? Well, the logs always equal the exponent, so it's k to the 12th power, and the exponential is equal to the argument of the log, so it's equal to t. And then, again, there's nothing really to solve here, we're rewriting it, right? That's what it's asking us to do. If I asked this one, if I said natural log of 5 equals y. So this is a log, right? ln is the natural log. We actually wrote it above. So what's the base for ln? Well, the ln means log base e. What's the exponent? The exponent is what the log is equal to, so it's y. And then the exponential that we've created is equal to the argument of the log, so it's equal to 5. So you get e to the y equals 5. So knowing how to rewrite logs as exponentials is pretty important. It's also important to be able to go the other way. All right, so if I said, for example, rewrite each as a log, all right, here we would have an exponential given to us. So if I wrote 5 to the 4th equals 625. Now remember, logs are always going to be equal to the exponents. So when we go to rewrite this, the easiest way to rewrite this probably is to think about, we know it's going to be log, and then ask yourself, what's the base? Well, in here the base is 5, so it's log base 5 of what's the argument? Well, the exponential is always equal to the argument, so it's log base 5 of 625, and you might see this in parentheses sometimes, it means the same thing, is equal to, what's the exponent? Because logs are always equal to the exponent, what's equal to 4. And again, there's nothing else to do here, we're just rewriting. But having an understanding of how to go back and forth between the forms is important. If I said, for the next one, if I have e to the t equals k. Well, again, we know we want to write it as a log, so I'd start with log, and then ask yourself, what's the base? Well, the base here is e. So it's log base e, which in a minute we'll rewrite as natural log, because log base e is natural log, but it's log base e of Well, what's the argument of the log going to be? It's equal to whatever the exponential is equal to. So it's log base e of k. And this equals, remember, logs always equal the exponent, so it's equal to t. Now, this is fine and good, but when we say log base e, we usually write ln. All right, so ln of k equals t. And that's really how you want to write it. Don't leave it as log base e. There's a natural log button on your calculator. That's one of the reasons why you want to write it as ln. The other reason is because, it's just mathematically sound. But knowing that log base e is always natural log. What if I wrote this? 10 to the second power is equal to 1,000. Well, we want to write it as a log, so we have a log. What's the base? Well, the base in this case is 10. That's actually a special base we'll talk about in a minute. So it's log base 10 of what value? Well, it's whatever the exponential is equal to, so it's log base 10 of 1,000, and it's equal to the exponent, which is 2. Now, one of the things that you should know, this is important, is log base 10, we just write as log. So if you see log without a base, we assume it's base 10. This is log of 1,000 equals 2. And that's how you would write it. So just as a note, right, log without a base shown is considered to be base 10. Right, and that's something you should know, right? So log without a base shown is considered to be base 10. So if you just see log, we know the base is 10. If you just see natural log, ln, you know the base is e. And then any other base, you'll see. On your calculators, typically you'll have a log button, log. Log means base 10. ln, natural log, means base e. You should know that when you see those. Alright, so now that we know how to rewrite as a log, we're going to use log properties to help us solve, but I'll include that in the next video.